Thanks, guys, and thanks everyone for coming. So, like I said, I'm Robin. I just want to thank the organizers, Anshan, for the idea of doing this, first of all. I would have not thought of it. And Hive, thanks for having us. Also, the researchers that I'll talk about in this publish openly, and that's kind of a big deal. So my aim for today is to bring you what things that I've been learning about reinforcement learning and make it easier for you on your journey, hopefully.
Sorry, Rob, are you sure you're on and loaded and
Check. Thank you. So I really went through a lot of reinforcement learning material to put this together in some original content. I have found there's a ton to know. RL is huge. These days, like contemporary RL is very vast. So I hope that other people get inspired and come and present something on RL, and let's share and figure out all the other stuff. I have some other RL talks that are partially done, so I'm hoping I will come back and continue on this train. But I'd love to hear from other people too. So I already said about my role. I have a BC-based consulting company. I'm not representing Ag Funder today. This is my personal interest project, reinforcement learning. But that is my day job at Ag Funder. And in the past, I did a technical PM role at Microsoft, worked in transportation, high-performance computing, in environmental engineering, and I'm a grad at Waterloo. So I heard something from you guys about your roles, but I wonder who here deals with machine learning in their job? Can you just see by show of hands? Okay. Does anyone feel comfortable with reinforcement learning? Okay. And anyone written some RL code at all? A few people? Okay, great. A little shy, I would say. Don't be shy. I can't wait to talk to you about it after the talk. I'd love to hear more about what your angle is on it. Okay, I made too many slides today. All right, so I could either blaze through them, or I could go at whatever regular speed, and we might not get through the whole thing. So the way it's structured is the first half is more general introduction to RL, and the second half is Q learning and deep Q networks, like more in depth. So does anyone think that I should go anyone not think I should blaze through the whole thing? Really? So you'd be okay if we didn't get through all the DQN stuff? Okay.
Well, you do have a sequel coming up.
That's a minority of people, but there's some people here. So let's just see how we do, okay? Okay. No, I really wanted to work for you guys, because that's kind of the point. So I'll kind of go fast, but I won't skip stuff, and we'll see how it goes. So reinforcement learning is... My friend who's an artist, she asked me, hey, you're giving this talk, what is RL? And I thought, how am I going to explain to her, what is RL? And so the best analogy I could come up with on short notice was, you have a new puppy in your house. You communicate with the puppy with you pet it if it does something good. You give it a stern look if it does something bad. And that's kind of all the communication you get with this creature, right? So on a basic level, it's trying to get the behavior you want with very, very minimal input. It's not like supervised learning in that way. Yeah, something's like this. Okay, so there's three main legs of machine learning: unsupervised, supervised, and reinforcement learning. It's usually spoken of as the third leg of machine learning. It has some things in common with supervised learning because there is some type of supervised signal, that's the reward, but it's much less information in terms of supervision than supervised learning. So it can be very, very minimal. Consider AlphaGo or AlphaZero. It's a very complex game. And in the end, the system only gets one bit of supervision. Did you win or did you lose? And an incredibly complex behavior has to be pulled out of that one bit of information. So it's kind of a different level of, you guys can just look at me if you want, because there's nothing going up there until it's fixed. There's one, think about the difference between supervised, right? Having to have all these labeled examples. So you can't train a puppy that way. You're not going to show a picture to the puppy of all the things that it should and shouldn't do, right? So does anyone have an RL project that they would mention to me, something they're working on? I saw a few hands of people saying that they had something that they're working on.
Price prediction.
Okay.
Grid world navigation.
Okay, and what phase are those at?
Finished, but I didn't get my million stupid stock price prediction one.
Did you learn something?
Yes, stock prediction is hard.
Anyone else want to share something?
So I'm starting a project to look at chemotherapy of button cooking. So scheduling from.
With RL. Very interesting. Thanks for sharing that. And then I can say I'm working on, and I hope to present that in my next talk. I'm calling it AlphaZos, but it's a game playing reinforcement learning system for kind of arbitrary board games. And I'm starting with fairly simple board games, but it's using self-play. So the goal of that system was to explore the concept of self-play. I guess when I heard about AlphaZero last year, I was very curious. How did they do that, right? What are the properties of self-play? It's kind of a strange and interesting thing on its own. All right, so compared to the other types of machine learning, right? What's different here? Well, one thing is we're not given data. We have to decide how we're going to explore to get the data we want. We're exploring the environment, and how we explore is kind of a huge deal in RL. That's not even a concept that makes any sense in supervised or unsupervised. But what I discovered, exploration is really key to RL. And the reward is just this sparse delayed reward. That's all we get in terms of labels. We don't get this explicit label, per example, like we do in supervised. Or even you might say hey, what about semi-supervised? Is anyone familiar with pseudo-labeling, semi-supervised? Yeah, that kind of seems different, similar, because in some cases you have no labels. But it's kind of not the same, because imagine like the very first move in a Go, right? You don't have any label for that. There's no sense of you have nothing to go on except what you've learned about the sequence of events leading you to a final state when you finally get your reward. So it's not like you couldn't pseudo label that first move. It doesn't really make sense. It's a slightly different thing. In terms of evaluating reinforcement learning, it's also a slightly different world. You're looking at the total reward you get. You have a concept of regret, like how much reward did you miss out on by not acting perfectly from the beginning. And then in terms of training and testing, you don't have data for your training and testing. You don't have a data set given to you like typically you would in supervised. What you have is a policy that you use to do your exploration, or a policy you use to, when you finally trained, to actually perform. So supervised learning, or reinforcement learning, is postulated to be the mechanism used in animal brains. And you can see here it's the basal ganglia using dopamine that it handles the reinforcement learning. You can see here the brain combines all these different types of learning. So this is a slide from Jan LeCun. He famously said, machine learning is like a cake. RL is the cherry on top. There's been a few different opinions about exactly what he meant, but if you see here, he's talking about how many bits are being predicted by the machine for each of these types of ML. So and here, by the way, unsupervised, he's talking about like predicting the next frame in a video, where you're predicting like a lot of pixels, or predicting the next word in like a Wikipedia. Your model is learning in an unsupervised way how to predict using the data. So there's a lot of data that it's predicting. And then supervised learning, what the machine is predicting is just the labels, so it's smaller. And in RL, it's predicting a lot less. So that's why it's the cherry on top. He also said that this was offensive to reinforcement learning people, which I didn't really understand that comment. But he likes RL, so I don't think it was really offensive. It's related to a lot of other fields. What I find interesting here is in engineering, because my background is computer engineering. It's related to control systems in a sense. Also in economics, it's related to game theory. It has like a different, all these things are different ways of looking at making decisions under uncertainty or control. So when to use RL? So in general terms, if you know what a good or bad result looks like, but you're not sure, it's hard to describe how to get there. Like when you look at a Go board, if you know the rules of Go, you know if you did well at the end of the game. But how to describe how to get to that point is really hard. When you need tactics and strategy, again, you need action and a series of actions. And you're not just predicting something. So different cases, games definitely have been explored. OpenAI and DeepMind are doing games. Complex robot control, there's been a lot of work out of Berkeley about controlling these types of robots using RL. Why RL? Because they have so many joints with so many torques. And if you want the robot to pick up that and put it there, it's actually quite a complex program. So right now they hand code all of those motions, and that's very time consuming. So to train it to pick up that instead is like a big deal. So how can they make robots this complex that don't require a lot of hand coding and can be quickly reconfigured for different tasks? They're trying to apply RL to that. It's a challenge. Okay, dialogue systems. Yeah, Facebook has a system that they use for testing where they're training RLs for like chatbots. And that's kind of a common application. I believe that Google Duplex, the phone system they just released, is probably using RL or used for training, although they haven't said that publicly. But I think it's probably the case. I suspect, anyway. Vehicle control, that's an interesting one. I mean, you might think, like the MIT, self-driving car course has like a deep reinforcement learning for driving thing, and it's like, make your car go on the highway and not crash anything. I mean, is it really practical? I don't think so. Like, you want to know what your car's doing. You want to know why it's doing what it's doing. You don't want it doing some kind of exploration policy. I mean, I think end-to-end RL isn't really practical in the real world for that scenario at the moment without a whole lot of special consideration. And that doesn't seem to be how they're really doing it today. But definitely, RL and deep learning are both advancing, and the scope for applications is growing with that advance. So you'll see this list grow, basically. So it really helps if what you're doing is simulatable. If not, you have quite a difficult problem. You might be able to do RL based on existing data, but most applications you see are simulatable. That means there's an environment where you can test all sorts of policies and exploration. So for the big RL projects that you hear about, AlphaGo, the OpenAI Dota, these things like the DQN Atari, they can play those simulations as many times or millions of times as they want because it's all perfectly simulatable. Getting an RL in the real world is not perfectly simulatable. You can simulate it, but not in a perfect way. When you're playing Go, you can simulate it in a perfect way. Like, there's no details of the real world that cause your simulation to differ from the real world. That's kind of a big deal. If you have big state spaces that you need exploration, that could indicate you would have a good problem for RL. If you have a small state space, there's much easier ways to solve your problem. You don't want to use RL unless you need to. Dependencies across time, if you have like things happening that depend on what happened in the past, in the future, sequences of actions. So don't use it unless you need it. It's right now, it's not very mature, it's complicated, and it's very data hungry. But it's fascinating. And these things are all being worked on. So speaking of data hungry, this is a slide from OpenAI showing the latest AI projects and how they're growing in the compute needed for the project. Since 2013, okay? We're going to talk in depth about ZQN today, but look at how this has grown. You might recognize some of these names on here. The green circle ones are RL projects. Okay, this is 1 day of compute on the world's fastest supercomputer. That's a huge machine in China. Okay, this is a log scale, by the way. So that's a gap of 10 times 10 every big step there. So you can see, like, that's a lot of compute, right? So 4 of the 5 most data-hungry AI training runs happen to be, at this time, reinforcement learning. Very data hungry. Oh, and this is 1 day on the new NVIDIA $400,000 machine. That's at that level. And that doesn't get you very far. So let's be really open about hype versus reality. There's so much hype around this stuff. And when people say they're scared of AI, they're really probably scared of RL because, PCA doesn't do anything, right? K-means is not going to take your job, but RL actually might if they figure out some of these issues. On the other hand, there's really not many applications in the real world yet, and it's not very fast to learn. Generally, that's one of the research. That's one of the focuses of research ongoing. It's of questionable practicality for real robots. Like, a lot of people hear about when they think of the most advanced robotics company, they might think of Boston Dynamics. They do not use this. They don't use anything close to this. If you watch the MIT AGI class from last year, the CEO of Boston Dynamics was on there, and he's saying, and there was a question from the audience, do you use deep reinforcement learning? And he said, we don't use learning. So it's, and they got really impressive results, right? People are afraid of their robots because they're so good. I mean, are they really? I don't know. They're good at demos anyway. But it is progressing very fast, and I'll talk more about that soon. So on the hype side, this is David Silver. He's kind of the brains behind AlphaZero and AlphaGo. He's the lead of reinforcement learning research in DeepMind, which was bought by Google, and I would say they're kind of the leaders in this space. So he says reinforcement learning plus deep learning equals general intelligence. He's talking about AGI here. I think that's a pretty big claim. And then on the other hand, we have Andrew Ng. What does he say? He says there's too much hype. There's so much PR, and there's not really much deployment today. And that's totally true. So he doesn't sound like he's so excited about RL. On the other hand, his thesis was about reinforcement learning, controlling helicopters using reward shaping. So, I mean, he knows what he's talking about, and that's absolutely true. But he's also not really talking about, how it's going to look in 5 years in this quote. So I would say it is on fire. If you are following the research, this is the biggest deal right now. All this stuff is kind of like deep learning is moving ahead, hardware is moving ahead. You guys all know that. But reinforcement learning research is making fundamental advances in the methods used for reinforcement learning all the time. Like all the time. So you have to basically read archive nonstop to keep up with this stuff. And it's not just, new types of deep networks. It's like the fundamental algorithms of RL. So in terms of who is active in this space, I mean, there's tons. I can't list them all. I don't know them all. But I will say that the ones that I'm most excited about, definitely DeepMind is on another level with this stuff. They have a really big team, really big budget. They have a lot of really great minds working on all sorts of different angles of RL, and they're breaking new ground all the time. OpenAI is a much smaller project, but they have some interesting results as well. University of Alberta is actually an interesting case. The godfather of RL, Richard Sutton, is from University of Alberta. So we'll see many of the key researchers at DeepMind and other places worked under him. So U of A is like a big deal in the world in terms of RL. Google Brain Project, not so much. Berkeley does a lot on the robotics side, CMU robotics. And so I just want to take a moment to highlight, I forget who did this. It's using LSTM to learn Doom. I mean, to me, what these things say is like you got to know that the military, is looking at this and be like, when can we buy this? And I mean, it just brings to mind all sorts of issues in terms of when we have these really smart systems. How are things really going to change? And I think the path is very clear that these things will happen, and changes will come, and some of them we won't like. And when the changes do come, when these systems really are making it to the real world, it may be kind of late at that point to start thinking about how we as a society deal with that stuff. So I just want to highlight here, we have a great organization in BC. They're the leaders in Canada, the BC Civil Liberties Association. And I think they're really worth supporting. They only have 2,000 supporters, which I think is ridiculous. There's no other province has something like this. I would say they're one of the best organizations in Canada in terms of protecting our rights as citizens. I mean, if you think about like police forces and militaries and stuff having all sorts of it'll bring up all these issues, and I think we need to start supporting these organizations earlier rather than later. So my point here is, with great power comes great responsibility. That's a Spider-Man quote, right? And I really do believe that. These things kind of are toys right now. It's kind of like a toy, but it's a toy that's going to turn into something. It's going to jump out of the lab all of a sudden in the not too distant future. And if we understand it, we'll be in the minority who understands these things. So I think it's important that we think about our responsibility in that way. We're the minority who understands what's going on. So let's get a little more formal. Reinforcement learning systems generally starts with this diagram. This is from the canonical book. This is the canonical book, by the way. If you're interested in the topic, you should read it. So the main components are an environment. It's a very general term, environment. An agent, which is what we are trying to, in reinforcement learning, we're generally trying to train an agent to act intelligently in this environment. The agent gets percepts, like it gets to see things in the environment. It gets to witness the state of the environment. It gets a reward signal from the environment that indicates how well it's doing or it did. It takes actions. And so this loop just continues. This is like the clock cycle loop of an RL world. So to get to the point of understanding the core of RL, the simplest starting point is the Multiarmed Bandit. So unlike a real casino, in this scenario, there's slot machines, and each has a different probability of winning. And you don't know what they are. And so you're presented with them, and the question is, okay, what do you do? Well, you try a couple, right? Maybe get some wins, maybe get some losses, and you're trying to maximize your winning, and you're trying to minimize the time you're messing around just figuring things out, right? You're trying to minimize your time, wasted pulls in the exploration. So here you can see posterior probabilities after a certain number of pulls. And the more evidence you have, the more times you pull the different levers, you start getting a clear picture of which ones have good payoffs and which don't. And once you know that, then you don't go to the ones that don't pay off. You just keep pulling the ones that pay off. But in the beginning, you cannot know. So this is the fundamental, a fundamental thing about RL is the dichotomy between exploring and exploiting. Exploring means, hey, let's try a new restaurant tonight. It's a little risky. Maybe the restaurant's no good. Exploiting means, let's go back to my favorite restaurant again. I know I'll have a good time there. There's no risk, but there's also a limit to your reward. You know it's not going to blow your mind. You know it's good, but it's not going to surprise you in how good it is. That's a fundamental thing in RL. Explore versus exploit. If you do either one alone, you're probably not going to get the best results. If you just are always exploring, just trying different restaurants nonstop, your risk of having a not ideal experience is pretty high. If you just keep going back to the same restaurant, you're not going to necessarily find the best. So supervised learning, cannot solve this problem because it doesn't have a concept of exploration. It doesn't make sense in supervised. So now let's take that same scenario and let's add a context to it. So you still have the 4 slot machines, but now you actually have 2 sets of 4 slot machines. One is at this casino and one is at this casino. Now, and you get to know the state. You get to know what state you're in. So now the action, like pulling lever 2, it means something different if you're in the other state. Obviously, right? It's a different machine. But you still have the same bank of 4 machines. But now you really need to know what casino you're in to know which distribution you're dealing with. Okay, so that's adding adding the idea of a context to your action selection. Oops. Now, to get to the what's called the full reinforcement problem, so the 3 steps are Multiarmed Bandit, it's only in one casino. Then you add the states, that's Contextual Bandit, that's having multiple casinos. And then now you go to the full reinforcement learning problem, in which your context can change depending on the action you take. Now this doesn't really work in casinos. You don't get teleported to another casino if you pull a lever, but in RL, you can change states depending on what action you take. So there's this thing called an MDP. We'll get to that in a second. Actually, let's do this slide. Okay, so very briefly, we had the Multi-Armed Bandit. And to figure out what to do in the Multi-Armed Bandit, we have to learn the model of outcomes. We have to learn something about their options. Once we've learned it, then we move down here. Now we're in decision theory world. Now we can just decide which arm we want to pull to get what reward. After we've learned, we can just decide. In reinforcement learning, once we do reinforcement learning, then we've learned about what's called the Markov decision process, which represents the environment. We'll get into that in a second, the details. So in, what was I trying to say here? Experience effects. Oh yeah, so in terms of the environment, the agent experiences the effects of the rules, like winning or losing the game or getting a certain reward, but it doesn't necessarily know the rules of the environment in advance. It doesn't know the rules. It's exploring to figure out what those rules are. Sometimes we don't really know the rules. So to understand what a Markov decision process is, let's start from Markov chains. This is a more elementary thing you probably heard of in data science. The key thing is the Markov property, which means the state that you're in fully defines your history. You don't have to know how you got there, what happened before. You just have to know if you're there. That's all I need to know how things are going to go from here. I have a couple options from there, different probabilities. So you have transition probabilities between states, and the transition has a destination. So these are states, and these are transitions. Okay, very simple. Now, a Markov decision process takes that one step further. So it takes a Markov chain, and it adds a concept of actions and rewards. So now you're in a state, you take an action, you can, and then based on that action, you have some probability of going there and some probability of going there. And in some cases, you take an action, and a reward comes out. These are rewards. So you have those two new components, actions and rewards. And so added to simple Markov chains gets you MDPs. And then there's some interesting variants of MDPs. Like a bandit problem is an MDP with only one state. Very simple. You have actions and they just loop back to themselves. If you have a Markov chain plus rewards, you get this other thing called a Markov reward process. And then you can have partially observed and semi-MDPs. We won't get into that. MDP exists in this kind of different, there's this world of related kind of mathematical objects. MDP involves both choices and fully observable. And you can see Markov chain is a simpler version. If it's partially observable, it's called a partially observable MDP. And hidden Markov models is in that set as well. So the reward signal, let's talk about that. That's, honestly, this is so crucial. Like I said, Andrew Ng's thesis was about about the reward signal, shaping in his case. But the reward drives the learning. The details of the reward are critical to how your system is going to learn. If it's sparse reward, then learning might not ever take place. And I'll show you an example of that later. And if it's too easy to get reward, then your agent's not really motivated to develop sophisticated strategies if it's getting rewarded too easily. So there's kind of some kind of balance here. How you define the reward really depends on your problem, and your system will try to game the reward. It'll just try to find ways to get the reward that you didn't think of too. So let's look at Montezuma's Revenge is one of the Atari games. So Atari, DeepMind kind of revolutionized this whole field. In 2013, 2015, they came out with a paper where they made one algorithm that solved these games. However, a few games it couldn't handle. Like, there's a giant list of games, and it solved most of them. But Montezuma's Revenge was kind of the hardest. And if you look at the difference between Kung Fu Master, if you just wiggle the joystick and do some kicks and punches, you'll probably do okay. You're getting points, right? You're getting a lot of points. So it's getting reward signal. By the way, that system worked on getting, the reward is the points. Montezuma's Revenge, on the other hand, is a game where you have to go through this maze of screens and do very complicated actions like take a key from way over there and bring it to way over there. And these systems have a lot of trouble with that. So the original DQN paper, they did not solve Montezuma's Revenge. This graph is terrible. This is awesome. They solved Pong, right? But Montezuma's Revenge, they really didn't get anywhere.
What is this graph? What is it?
Yeah. So thank you for pointing that out. So along this axis is how much training they gave it, like how many frames or millions of frames that it tried. And the vertical, it has to do with how well it was performing. And Montezuma's Revenge really didn't get anywhere. So this formulation that I talked about, the agent environment, the MDP, and the reward, these three things, if you really deeply understand these things, they can be used for a very wide range of scenarios. So you can have environments that are of finite length, like a game of chess, or of infinite length, like a robot that goes to Mars and just stays there for 1,000 years. There's no end to it. There's no score at the end. You're not waiting to see if you won. There's some environments where you get rewards just for continuing to survive for every cycle. You might get a reward for how long you're able to survive in the world. You might get a negative reward for how long you're having to stay in that world. Like, for example, if you are in debt, you might get a negative reward for every step you stay in debt until you get out of debt, and then you stop getting that penalty, right? So it's very flexible. Action spaces could be discrete or continuous. That means in a board game, usually you have a discrete set of choices, but in a robot controller, you're controlling an arm, you have a continuous control signal, basically. You're not picking one action, you're picking a value, continuous value, or a large set of continuous values. There could be just a few or a huge number of actions at every step. The state space, it can be quite diverse. So we're talking discrete or continuous. Continuous actually is a little bit of a special case. But you could have state spaces that are trees, like some games might have like a tree. You can have graphs, like with cycles, you can come back to the same state. They can be deterministic, stochastic. It can be partially observed. So all of these variations, reward signals, they can be just stochastic too. There can be some randomness in how you get your reward. It doesn't have to be deterministic. You can have continuous, that means you get a reward for every step. Maybe it differs in its size, or maybe it doesn't. Maybe it's more about how long you survive, or how long you are stuck there. You can get rewards right away, or maybe way later. Like in Go, you get no reward until the very end. But in some environments, that's not the case. So what I'm trying to say is, depending on your scenario, you can couch it in this very flexible framework in different ways, and the framework is quite flexible. It can help you in a lot of different ways. So the basic framework for thinking about different types of RL algorithms, a simple way to look at it is policy-based, value-based. I would say those are the two main distinctions. Value-based has to do with having estimations of how valuable it is to be in a specific state. How good is it to be in that state? Like, for example, in a board game, the state right before you win, if you make just one move and you win, that's a good state to be in, very high value. The other state that's right one state before you get beaten, that's a terrible state to be in. You want to avoid that. Anshan?
So when you say a state, is it the same as a state in a Markov chain?
Yes. Yeah. And you can define that however you want in your problem.
You should repeat the question.
So the question was, is the state the same as what we were talking about in a Markov chain? And the answer is yes. That's the state. And then policy-based is directly constructing your pi function. Pi function is, if we're in a state, what's our policy means, what action should we take? So instead of thinking, okay, how do we value all the states, and then thinking, now how do I get into that good state? That's one way of looking at it. You've separated the problem of action from thinking about the states. The other way, the policy-based way, is just to say, look, just tell me what to do. I'm in a state, just tell me what action I should take. It's not, policy is not trying to decompose the value of the state from the action. It seems a really subtle and small difference, but it's actually kind of a big deal. And then model-based is a whole different thing. Model-based is trying to learn the structure of your MDP. Which, remember, when your agent first gets introduced to the environment, it has no idea what's happening. It doesn't know the MDP. It doesn't know what states there are. It doesn't know what transitions happen. It doesn't know what actions cause what rewards. It doesn't know anything, really. It's basically tabula rasa, blank mind. So some systems don't even try to learn all that stuff. They try to avoid it. But there's some pros and cons to trying to learn that whole MDP. You can imagine the MDP is like a giant graph. And you can learn how to navigate it, or you can actually learn the whole thing. Yes?
How do you initialize the model? So, you said, I don't know how many states there are. So would I keep building my state space?
So how do you initialize a model? If you don't know how many states there are, how do you proceed? So does it depend on the kind of RL? How do I answer that question? You kind of don't really worry about it. You just, when you experience a state, you're like, oh, I found another state. I mean, if you try to keep track of every state, if you explicitly keep track of every state, you might get a ridiculously big list. Like, try enumerating all the states on a Go 19 by 19 Go board. You won't be able to do it. Model-based will try to make some kind of approximation of that. So you might have a neural network that's trying to kind of approximate your state in some way that's a smaller, that can fit in your memory of your system. I don't know if that answers your question. It might come clear later. The other thing is, in terms of initializing these systems, sometimes they just start random, like with a neural network with random settings, and they just start training. And if you still have this question later, let me know. So there's kind of this concept of planning versus reinforcement learning. Like if you knew your whole MDP, then you could use some old school planning methods, like heuristic search, and say, okay, how am I going to traverse this MDP to get where I want to go? That's actually, we know how to do that, right? That's not hard. But you can only do that if you know your state space. And in RL, we don't really know it. So if you do know it, or if you can find it, or if you figure it out, then this can be a promising way. And there's ways to combine these two approaches. There's actually many different ways of combining these two approaches. So in a rollout, this is called a, so the planning would be like this. You have all your states, you're like, oh, I know, I'm trying to get to there, I guess I could go that way. And you're planning, you're just going through in your memory and traversing these. Like it becomes like a navigation problem, right? In reinforcement learning, generally when if your agent is having an experience in the environment, it produces what's called a rollout. A rollout is like one experience through the environment. So this rollout, in this particular rollout, they happen to go from this state, the agent chose action 1, got a reward 1, ended up here, blah, 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 blah. So that list of that experience as a list, as a set, is one rollout. So then typically they do a number of different rollouts, and from those rollouts they're learning something. So the most elementary kind of straw man, not necessarily straw man, sometimes they're very practical. The most basic approaches to dealing with the RL problem is these three. So Monte Carlo is basically, let's just jump in there and do some random choices and see what happens. Make some rollouts. Just try it. And at the end of the rollout, you remember what the reward is. And you just keep doing that. Actually, AlphaZero does that internally. A variation on this. It just tries a bunch of things from a certain state. Then there's also value iteration and policy iteration. These are kind of, all these you can't really do unless you already know the transition, like you understand the MDP. If you know the MDP, then you can just keep iterating on these or on dynamic programming. Dynamic programming solution would be like, hey, I have a grid world, I have an end state. Let's be smart about this. Let's calculate the value of the squares 1 away from the end state. That's easy. They're just 1 step away. Now let's go back 1 more step and say if we're 1 step away from those, we can figure out, oh, it's just 2 steps because we know where the goal is. We're 2 steps away. That's easy too. And then we keep backing up until we get to the beginning, and we're like, oh, now I know how far it is to the goal, right? I know how to proceed. So it's kind of like a very simplistic way to look at it, and you do need to know the MDP, which we normally don't. So normally these types of approaches are not directly applicable, but they're useful in a conceptual way to think about. But Monte Carlo is a reasonable approach. I'm not going to walk through these. You can look at these later. I don't think you would do this in real life, either of these, value iteration or policy iteration directly, but they're kind of like a starting point for better algorithms. So you can, just very briefly, you can see, am I really going to do this? I'm not going to do this. I have too many slides, guys. Okay, so let's look at there's another way of looking at the different types of RL algorithms. They vary in different ways, right? There's some handle discrete actions. Some can handle continuous. Some are model-based or model-free inherently. Some are on or off policy. I'll describe what that means later. Some require taking derivatives of your policy or something, and some don't require that at all. Like these are DFOs, derivative-free optimization. So if you fill this in, these are different. Each of these is a different algorithm or a different approach to solving RL. So down here are specifically model-based methods. This section down here is basically separate from up here. Then there's planning. Remember we talked about planning. You can combine planning and RL. Imitation is where like an agent's is like watching you or watching another agent and saying, gee, what is that agent trying to accomplish? And trying to copy them. Not necessarily by copying their actions directly, but trying to copy their motive. Hierarchical reinforcement learning, it's quite diverse. Some of them have memories, like they remember past experiences. Some of them have imaginations. This is quite an interesting one. They can actually, once they've experienced the MDP, they can imagine different paths through the MDP and actually learn from their imagined experiences, which is sounds kind of strange. And then some are more focused on general, like learning in a general sense, and some are very really focused on mastering one environment. So there's the dichotomy between learning between different environments or really mastering one environment. Like sometimes researchers are going for one or the other. And then I added a whole bunch more. If you start reading in RL, there's a lot of algorithms. And I wanted to try to understand this galaxy of stuff so I could figure out which ones I really want to learn. Today, we are going to be over here. And we'll talk a little bit further around that, but we're really going to focus on DQN. I think DQN is a really the perfect starting point to start to understand this stuff, and then we can get into other stuff as we go. You don't have to understand all these to get somewhere in RL, but if you understand the general landscape, then you know where to look for different things. And like I said, there's new ones coming out all the time. So how do they work technically, and when you're looking at RL paper, what are you going to see? You're going to see these, and you're going to say, if you don't know, you might say, well, what are these functions? So let's walk through them really quickly. We already talked about V, the state value function. How good is it to be in this particular state? If you're one step away from winning, that's a great state to be in. You may have got 0 rewards still. Like imagine a board game. Imagine tic-tac-toe. You don't get any reward to the end, but if you're one step away from the winning and you're about to get that one reward, that's a pretty good place to be. You still have no reward. You've never gotten a reward. It's still very valuable because you're so close to getting that. Now, a state action value function is kind of similar, but puts a little different spin on it. This is what we're going to use today in DQN. And that's saying, if I'm in state S, how good is this action to take? So that's kind of saying, it's almost like saying, what's the value of where I'm going to end up? It's pretty much like that. It's pretty much what's the value of that state I would end up if I take that action, right? So that can be when you're one step away from winning, that might be a pretty good state. But if you make the wrong move, it's still you could still lose. So this is a good state to be in, but that would be a bad action to pick from this state. Right? If I just take one more, I get my point, but any other action makes me not win. So even though that's a good state, I could still screw it up. Now, policy is a slightly different thing. Policy is, it's a function of your state, and it just gives you the action directly. So not thinking about the value of the action, not thinking about the value of the state, just simply, what should I do? Okay, I'm here. What should I do? Look, just go there. You'll win, right? They might not know you'll win, but it might know. When it's trained, it should know that that's the best thing to do now. Yes.
Actually, say a policy is like conditionally independent of other states. So when you say you want to learn a policy and what action do we take, the state has, and you start saying I'm agnostic to the value of that state, and I'm conditionally independent of the other.
I'm sorry, I don't fully understand the question. Okay. But the policy would give you a different result depending on what state you're in, right? Now, advantage function is kind of combining the value. Well, what it's saying is in a state S. So if you're in a certain state, it could be a good state or it could be a bad state, whatever it is. advantage is saying, relatively speaking, given that we're in this state, is this a better move to take than this? Right? It's kind of, it lets you compare different actions. So the reason this is useful is, in some cases, it's really hard to estimate what the value of this state is. It might be really hard to get that value, that number. But it might be easier to have a relative measure of which action is better. So even though I can't really calculate how good a value this state has, still I can tell that this has more advantage going this way than this. So some algorithms use that. Transition prediction.
So when we talk about transitioning to a new state and having better value, is the idea that we are kind of following a greedy algorithm? We want to maximize our value at every step, or not? I mean, we just look one step ahead.
In general, we generally will want to be greedy. Sometimes in training, we might not want to be greedy. Greedy in this scenario means just picking the thing that looks best from this point. So ideally, you boil down your whole problem so that you can just pick greedy at every step, and it works out great. In a lot of situations, if you do that without being really smart, if you do that without knowing, if you do that without extrapolating all the endpoints or the rewards from the future, being greedy isn't going to help you. But if you couch it in a way where your trained system can simply act greedy at every step, choosing the best thing at every step, and it gets to a good result. That's
Maybe why Montezuma was hard, because greedy doesn't really work.
Greedy is hard because reinforcement learning does a lot of random exploration to find out what the shape of the value functions are, as a general way of explaining it. And that's really hard when you're in a flat desert. Like Montezuma's Revenge is giving you no reward, so it's just flat everywhere until you get really far and then you find a peak. But unless you explore all over the place and somehow get to that peak, you're not finding anything, right? It doesn't have forward vision to see, oh, there's a peak in the distance. It just is looking down and going around and trying to say, how do I climb? I'm on a plane, how do I climb? Is that helpful at all? Okay, so transition prediction. These two functions are used in model-based. We're not going to talk about them today. But these are all critical. If you understand these, you can make a lot of progress in understanding a lot of RL algorithms. So RL algorithms differ in many key ways, but one of the most important is in terms of how sample efficient they are. That means how much experience do they need thrashing around in these environments before they get trained to be useful. In the beginning, they're really quite stupid. You watch these things in the beginning, it's like they're just thrashing around doing nothing useful. These are the least efficient, and these 10 times means 10 times more efficient. Right? So this is the most efficient. But some of these have conditions on them, like they're only relevant in certain scenarios. This Pilco, this super efficient one that's mentioned here, is really it's like a Gaussian process control of robotic controllers. So it takes into account the uncertainty in the model. It's model-based. But you can see at every stage there's kind of certain conditions that might apply. The gradient-free methods. This is kind of like random, almost like genetic algorithms, like just creating random neural networks and seeing, does this solve the problem? No. Does that solve the problem? I mean, it's a little bit smarter than that, but not much. So I'm not going to go into the details here, but you should be very aware that the sample efficiency is a big deal, because imagine if you end up at this level, how much you're going to require. You're going to be in a very different place on that compute graph in terms of how much petaflops you need to get anywhere. So what is OpenAI Gym? It's like the MNIST of reinforcement learning. MNIST being like the simple digit image, you guys know MNIST, for image classification. So OpenAI Gym is like, it's a set of toy problems that are used for testing RL algorithms, and so you can kind of, if you're trying a new algorithm or different ones, you can test it against a wide variety of different simple toy tasks. This particular one is, you have a controller that's controlling the joints of this robot, and the challenge is, how do you make the robot walk, right? If your controller isn't very smart, it's just going to thrash around, it's not going to even move. Just making it walk is a challenge. And this is showing after it's been trained. This is not a real robot, it's a simulated robot in a 3D environment that OpenAI Gym provides. And so you can plug these algorithms into this. This is an environment. The agent controls these, but this is an environment, and the reward has to do with how far you get. There's different variations, but like, how far can you walk, right? So if you imagine in the beginning, the spider's just flailing around, has no idea what's going on, it's not getting any reward. But it moves a little bit to the right, suddenly it gets some reward. It's like, oh, that seems like a good thing. It builds on that, and then over time, if it's trained well, it comes up with motions that are actually quite sophisticated. So there's a whole bunch of such environments or sets of environments, and these are very useful because they allow a common language between RL researchers. So like when you have when you're trying a deep learning, like a CNN or something, or an approach to image classification, you can be like, okay, well, how does it do an MNIST? Well, how does, that woman's system gets better on MNIST, so we should see why they're doing better or whatever. So it gives a common language between researchers. They can say, oh, how did you do on Carpool? How did you do on these other challenges? So OpenAI has Atari and Genesis, the old Sega Genesis games. DeepMind has a more recent one that's based on Quake. It's like a 3D environment that's used for multi-agent training. Microsoft has one based on Minecraft. Facebook has one that's text communications, like I think it's like chatbot type stuff. And then Vizdoom out of Poland. There's other ones too, but I would say OpenAI Gym is like the canonical one to start with. And so these different environments provide a different API, like a specific API for their environment, and that the agent can be plugged into that API. So if you set up your agent that way, then you can try all the different OpenAI Gym environments with your one algorithm. I mean, some of them have some variation, but generally the idea is having a common interface and letting you try different combinations. So let's look at the code. If this canonical starting point for OpenAI Gym is Carpool, what is Carpool? You're trying to hold up this pole, and holding up a pole is hard because it wants to fall over. So you're trying to compensate for it falling over. Your agent is moving left and right to try to keep this pole balanced, right? So it's learning. The longer it can keep it balanced, the better reward it gets. So it looks kind of like this. You can loop through episodes. You reset the environment, and then this is, for example, taking 100 steps. Rendering is just showing on the screen. That's optional. But here's a key step here. Take sample from the action space of the environment, one action. Now, this is just choosing a random action. And then the environment takes a step with that action, and that moves to the next time step. The environment returns the next observation, the reward at that point, the momentary reward, not the cumulative reward. Whether it's done, that means for whatever reason the simulation ended, which would be the case if it fell over. And then some info with just extra data. So you can see it keeps looping, right? Get an action, put the action in the environment, get the observation reward done, and then just keep doing that. And that's how the simulation proceeds. So all the complexity of the environment, the physics modeling, the reward signal generation, is all inside the environment. The agent doesn't have to deal with all that, right? The agent is going to make this part smarter. This one line can be as complex as you want. That's the agent picking the best action. So a little bit out of order, but this is DeepMind made another environment called StarCraft 2, and that's a much more sophisticated environment compared to the old Atari stuff. Their algorithms actually aren't able to solve this environment effectively. They can only solve tiny bits of it. But you can see, so they worked with the StarCraft creators to make an API that's suitable for AI, for training these systems. So here's an example of it's just something animated. So this is saying so StarCraft is I don't actually play StarCraft, but apparently it's a very sophisticated game of outer space exploration and conquest. And like I said, RL isn't able to make much progress in the full game, but they've made like small maps, like smaller missions, and their RL system, the current level of RL, is able to make progress in those smaller maps, and they have the bigger environment there as like a goal. Like they would like to research, they would like to advance their research to the point where they're able to make progress on the main game. Here is the, I think this is the Quake-based one. This is DeepMind's lab, whatever they called it, their lab. And so you can see this agent's trying to get rewards from the apples and try to navigate this maze. And you can see this is the internal signals of their networks, the value function, saying how good the state is, the different discrete actions that are being taken to navigate through this. This one happens to be trying to predict the reward that it's going to get. That's part of some algorithms. These auxiliary tasks are things that can help with training, even though they're not directly related to the goal. So here's one from, I think, Facebook. They are trying to explore houses, but it's a similar idea. This is, so this is TRPO. I think that algorithm is from OpenAI, and it's training how to walk. Obviously, I haven't gone too far here, but I mean, it looks kind of funny, but if you think the reward signal is how far it walks before falling down, so it doesn't have to look good. It just has to be able to do some locomotion. And so you see here, over time, it's getting better. This is the type of things you will see if you get into this. So what about in real life? RL, IRL. So like I mentioned, most of the results so far are in these what I call hermetic environments. That means like things that you can perfectly simulate. In some cases, because they are simulations in themselves, like Atari. In other cases, like Go, you can perfectly simulate it. The difference between sim and reality is a source of a lot of trouble for these systems. Little things so you'll train this robot arm and it's working great in the sim, and then you put it on the real system, and all these little differences add up, like slightly different friction coefficients than you're expecting, slightly different, maybe you didn't account for the friction of the air, or maybe something, maybe your robot arm gets a little dent in it, or has a tiny bit more weight. All these little things, you catch your foot on a little string on the carpet. I mean, we are designed to those things don't matter to us. We're always compensating for all this stuff. These systems have trouble compensating for that stuff. So with model-based RL, you can be way more sample efficient because you're really planning. You can plan, right? But the plan only makes sense if the model, which is based on the sim, really matches the real world. And if not, then the further you get into the plan, the more out of sync you are with reality. So that's a common theme that comes up when you read about model-based RL. And so then there's techniques to bridge that gap. But this theme, I think, is going to be huge in the next few years. If they ever figure it out, it'll be amazing, and we'll be in big trouble because all this stuff will just jump out of the lab. That's what's keeping all this stuff in the lab right now. I think one of the major things is this, the difference between sim and reality. And yeah, I thought that was funny. Okay, so like, what is the state of robotic RL right now? It's kind of lame. I mean, these researchers are brilliant people, okay? I'm not dissing them. They're geniuses. But the level that they're working at, like the stuff that they're trying to accomplish right now, okay, this is kind of 2016 era, some of this stuff. But it hasn't gone like way further since then. I mean, it's gone a little further, but so here we're trying to. This robot's trying to put dishes in a thing, in a dish rack, and not break the dish and get in the right place with just like using. I think this one is using camera, just with a camera, and most of these are generally just with a camera. So. So there's a vision problem of estimating. Okay, where is the rack? There's the grasping problem of how do I grasp the thing? How do I do the motion? How do I, all that motion, not break the dish, not put in the wrong place? This is not easy for current RL. This is a research. This is Google research, okay? This is, here they're trying to open a door, okay? Like if you saw a robotics competition in, I think it was 2015, and it was pretty humorous. Like you see, I probably should have put the video in, but you see all these robots from the top researchers in the world trying to do simple tasks like open a freaking door. That's like a big deal. Like the amount of things you have to worry about, because you don't know, I'm pretty sure they don't know exactly the shape of the door in advance, where the handle is in advance. They have to navigate to the door, the grasping motion, all this stuff. Robots are falling over, they're missing the thing. They're just like, it's all these little difficulties add up in an incredible way. If you've actually done robotics, I'm sure it's not a surprise to you. Here, they're just trying to grasp an object of their choosing. They're told, the arm is told which, I think it's told which object to grasp, and it's just using a camera. So it's having to translate between what it sees to then the action space of the arm and successfully grasp. Right? Seems like such a simple thing. We do it all the time. It's cutting edge research. Okay. All right. So let's get a little more applied. What is Q learning? Okay, this guy is the Q from Star Trek, from the Picard days, right? That's why I use him, by the way. Q function is the quality of a state, of taking an action in a certain state. Quality. Basically, how much reward can I expect in the future if I take that action?
So is that more than just getting the V of the next state based on that?
It's kind of like the V of the next state, but you don't need to know what the next state is. It's a little different in that way.
Yeah.
You don't have to know that this state links to that state. You don't know what's over here. You just know it's good. Or it's bad, right? And that can be that can simplify things sometimes. So yeah, from that state, if I take that action, what is my expected sum of rewards in the future? How much goodness can come out of that? And that implies a policy, to your point before, Bruce. It implies that you should just pick the one that's biggest. Take the action that will lead you to the highest expected reward. Sounds very simple. And it is. So the way that works is it uses what's called TD learning to find the Q for each state. So TD learning, some of this stuff is super old. Look at this Watkins 1989. And some of it goes further back than that. Some of the roots of RL are quite old, and then what happened more recently is they added the deep part to it, and that revived the field. But you have to understand this stuff, otherwise you're just more doing script kiddie stuff with the latest libraries, which you can do, and it's fun. But if you understand Q learning, then you'll understand how DQN really works internally. So Q learning is only good for discrete finite action spaces. That means not a huge amount of different actions at every point, and discrete actions. That means like not an angle or something. I mean, you can discretize your space and cut up a continuous angle for your arm motors or whatever, but it can make your problem explode in complexity if you do that. It often doesn't work out very well. So it's a model-free type of reinforcement learning, So it's naive about action effects. It doesn't know what the actions are going to lead to what states. It doesn't know how things link together. But it doesn't need to. It works anyway. It's kind of surprising sometimes. It's called TD0, temporal difference learning 0, which means it only draws reward one step each time. And we'll see what that means. It is naive. It is kind of, when you understand what it's doing, it can act smart, and yet it doesn't know what it's doing. I mean, I know the computer never knows what it's doing, but there's no concept or there's no model of really how the environment really works in Q learning. It doesn't try to understand how the world works. It just tries to understand at every state what action leads to what kind of values. It's
The reward is the expectation of all possible futures from the action.
it's actually the best possible. If you choose the best from then on, what can you get? So, yeah. So,
How do you estimate that?
how do you estimate?
In any, space which is, even like checkers or something, the space of all possible futures from that action.
It's huge. So we'll get a little more into the details of it, and then see if you still, like, I'll show the equations and stuff, and see how you think. Okay, so a Q function. I mean, you could think of your world, like your checkers game, as like a landscape maybe, and there's states distributed over this, and you're trying to get to the peak. You can think of it as like a hill climbing thing conceptually, right? You're trying to climb up to the best value to get the best reward. But Q learning isn't really structured that way. It doesn't have any sense of connecting states together. So it doesn't really seem like this when you're doing it. It seems more like this, where you're in a series of a state is like a room you're in, and the actions are the different doors, and you have no idea where the doors lead, but you have a little marker on top of each door, and every time you go through, you get your reward, if you get a reward, and you mark it on the door as you go through, and you walk through to some other mystery room, and you do it again and again. And you're leaving a little clue behind, which is you leave a clue on the top of the door of what reward you're getting as you go through. So it's a little bit like that. So this is a screenshot of Alpha Zos, which is a kind of... It adds the immediate reward to the delayed reward as well. We'll see the equation for it, and hopefully that will become clear. So in terms of how it looks, Alpha Zos, this is the kind of toy game system I built to try out some of this stuff. And this is playing tic-tac-toe. And this is the value of each action. This is the Q value. And so DQN is this guy. That's Dr. Theopolis from the old sci-fi show Buck Rogers. So you can see Dr. Theopolis. This is after Dr. Theopolis picks this square because it had the largest Q value. All of the rest are slightly less. And it definitely avoided these two because these have big negative Q values. And the reason is because in the way I define this game is if you try to play in a square that's already full, you get a big penalty because that's like not a valid move in the game. So this might help you visualize what I'm talking about. The door is like the action, and there's like a little marker on top of how good that is to go through that door. Okay, so this is DeepMind famously solved Atari games. Oh, we already talked about that. Here's them doing Space Invaders. The value function here is changing as it takes actions. So you can see that there's the action, the value function, the value function itself isn't really strictly needed in straight Q learning. But you have the Q function here is saying how good each of the actions are. Do nothing. I think that's fire. That's move left, move right. Move right and fire, move left and fire. So these are the actions on an Atari joystick. Okay? And it's rating how good each of these are. Notice they're almost all the same, but very small variations. And so it's going to choose whatever one at that moment has the highest value. And as it proceeds, these bars are all going up and down. And so as it learns, these bars are getting more accurately assessing the value of the different actions. When it's fully trained, it's playing like a pro. Just another example, again, for my AlphaZo system. In this case, we're playing Connect 4. And in this case, the actions are just picking what row you want to drop a piece into. So again, the negative value for playing, you can't play there because they're already full. Okay, so inside DQN is Q learning. Inside Q learning is TD learning. TD learning is kind of a basic building block of a lot of reinforcement learning algorithms. It's kind of a really simple thing. It's just a way of predicting future values. So you were talking about is it immediate reward or expected reward in the future? So this is how you bridge those two worlds. You're bridging the immediate reward and the future reward. TD learning brings those together. So let's see. Let me explain here. TD0. Yeah, I think maybe the next slide will. Okay, here. So the intuition with TD learning is you're like stretching the rewards through time, right? Like a reward you get at the end of the game, you start pulling it forward through the states, or backwards, I guess. And then by the very end, you want to have pulled it to the very beginning of the game, so it becomes very obvious in the beginning of the game what actions you take to get to the best place. So for example, imagine you're walking down a hallway, and you only get a reward of 1 when you get to the end of the hallway. I mentioned TD learning is marking on the door, right, as you go through. There's not the multiple rooms here, there's a hallway, but let's just say these are the different states, 9 states. So the first iteration through, you experience 0 reward and then 1 reward at the last one, right? But as you go through to that last one, you mark on the door that you got that reward. So then the next time through, now you have a hint when you're at the second last state. So after you've done 4 iterations, it's pulled that reward back 4 steps. And now when you're here, you already know that's a promising path. And by the end, after 9 iterations, it's pulled the reward all the way to the beginning. And now it's very clear that if you walk down here. Oh, and I should also mention, there's a discount function applied, an exponential decay. So future rewards are discounted. And that's a key thing that comes up in RL a lot. This is important because imagine if you got a constant reward every step, like a reward of 0.1 every step. And if you had an endless episode, you get an infinite reward, which doesn't make sense. But if you had a decaying reward, then you can handle those types of scenarios. It's also kind of saying like, if I can win the game now, I'd rather win now than get my reward a few steps down the line, right? How are we doing for time? Okay. All right. Should I blaze through or should I? Okay. All right. So the state space Bellman equation. I don't know how deep you want to get into this, but let's say here the point of Q learning is you make it's like an iterative function where you define the value of the current state in terms of the reward now and the expected maximum reward for the future. So you can see now you have the Q here and the Q here, and the reward which we know when we experience it. So as we step through this multiple times, it converges to the real Q value. So this is called the Bellman equation. That's decomposing the Q value into something you know now and something you estimate later. Those two pieces, if you iterate on those, then you end up converging. So based on that decomposition, then you make a for every iteration, you do an update. And this slide shows what the update is. So, but it's usually written like this, but I like writing it this way because I think it's way clearer into what it's doing. If you see what it's doing here is, okay, when I go through and I want to do an update, so alpha is a small number. It's like the learning rate. So let's say it's 0.1. So then 0.9 times the existing Q. So I'm keeping part of the existing Q value. And I'm adding an update that has the current reward and the discounted maximum future rewards I can expect from here. So you're moving the existing Q value towards the new Q value every time through. And if you keep doing that, it starts converging to the true Q values. And this is just spelling out the algorithm. Okay, this is important to know.
On the previous slide, when you're doing the update, when you run sort of the full simulation.
Yes.
All the way to all possible futures.
Not all possible. One rollout means one path through. Like you're walking, let's say if you're in.
And estimate the next step, you need to know what's the maximum. Yeah, right. The max.
You just choose. You look at the Q values for all the actions you have. And you just pick the largest. So for example here, you look at all the Q values here, and you just pick the largest. That's all you're doing. You're not having to experience all the futures. You're just saying from here. They're estimates.
And for all the states that you have, let's say for the full state.
For every state you walk through. Not every state in the world. Just the states in your rollout that you experience. Okay, so this slide is super critical. Okay, are you guys bored or are you having a good time? What's going on? Okay, do we have to shut down really soon? What's the rule on the time?
We all have to be out of here by 8:30. I just need help putting the desks back.
Okay.
So I'd say, yeah, we have to be out of here at 8:30.
Okay. All right, so I really want to explain this slide because it's key to everything. Q learning. So once you have these estimates of your Q values, there's typically in Q learning there's two ways you can approach it. One way is exploit. Exploit means pick the best. So here I'm going to pick here because I know that looks like it's going to give me the best result. The other thing we can do is explore. Explore means, look, I'm not really sure all these are right. Let me try some of these other actions and see what happens. What if I go there? And just explore that, but do a rollout, explore that path. That will update all the Q values down that path. And that will cause this bar to get a little more accurate. So as you do your exploration, you're not expecting to win. You're expecting to make all these values more accurate. So in your training process, you do exploration. And that means, generally, it means doing something stochastic. It means trying something. Trying something that you're not sure is going to work out well. It's maybe not give you the best reward, but it's giving you more confidence in your Q values, so you can choose better next time. So when you're training, you're doing this. You're spending some of your time taking random actions when you're training. When you're done training and you're like, okay, I'm ready to enter a tournament, you're not going to do this at all. You're going to always pick the best Q value. That's when you deploy, basically. So now I said pick a random action. There's many ways of picking a random action. You can just roll a dice and pick any old action, or you can like add a bit of noise to them and pick something, or you can do other things. There's a lot of different ways you can handle the exploration. But this is key to understand, and how you do the exploration is key to how you train. So that's called epsilon greedy. Epsilon greedy means, look, I'm going to choose the best action, but with some small probability epsilon, which might be 10%. If I roll a dice and I get under that 10%, then I'm going to just do a random thing. But with 90% chance, I'm going to pick the best thing. So, yes?
So for this what if we get like the same role that we had before? Is there anything inside of epsilon greedy to prevent the same role of, like, let's say, a single player game?
Yeah, what if you get the same roll from before? Vanilla Q-learning is not going to protect you against wasting cycles that way. But there's things you can do to make it a little smarter so it doesn't keep going down the same path. I mean, epsilon greedy itself the randomness is partially designed to keep you from doing the same thing, right? Depending on how complex your action space is, it might be actually really hard to do the same sequence of states multiple times, the exact same sequence. This, in the examples I'm showing, the states are so simple. They're so simple that, of course, you're going to keep coming on the same states again. But if you have the positions of a robotic arm, it's kind of unlikely that you'll just end up on the exact same states, right? That's a great question, though. And that is a real concern. On policy, off policy. Oh, gosh. So, on policy is like learning on the job. That means the agent is going to be using the same policy when it's deployed as when it's training. So learning on the job means watching someone do the exact same thing that you're going to do, meaning it's training. Its training policy doesn't differ from its actual behavior policy or target policy, which is what you're trying to, what you would deploy. Off-policy learning means when you're training, you do different things. You do a different approach than when you're deployed. Q-learning is off-policy because when you're training, you're doing epsilon greedy. That means when you're training, sometimes you do random things. When you're deployed, when you're done training, you never do random things. You just always are greedy. You pick the best thing at every step. Does anyone not understand that concept? It's kind of important. So certain RL algorithms you cannot handle, like generally they're either on policy or off policy. And there's on policy variants of Q-learning, but
on policy, you're using the same policy, but you're evolving it.
Yes, you are evolving it. Yes. You can still evolve it. Yeah. So very briefly, remember I said that Q-learning is a TD0 one-step method. So every time you pass through a door, you're marking that Q value, and that's informing the step before. But you're only informing one step in the past every time. And that's very slow if you think about it. So there's other methods where you can go and inform steps more in the past, and that usually results in faster learning. Okay, we're finally at DeepQ network. So what do you guys want to do? I don't know if I should try to blaze through this stuff or stop here and do another talk, or like I'd love to get questions too. I think we're going to get kicked out kind of soonish, right? So what should we do? I could do another. Yeah, I could split this into another talk. I mean, there's a lot of material, right? And it's honestly, I was trying to cut slides, but I'm like, if I cut this one, they won't understand. If I cut this one, I'll feel so sad.
Save it for next.
Okay, because I'll just let you know, I have another talk planned after this that is self-play, adversarial RL, multi-agent RL, Alpha Zero, and Alpha Zos, which is the game system I'm working on. So that set of things. It's focused on self-play. That means reinforcement learning that's playing against itself or a replica of itself, which is different. In Carpool, there's no self-play, right? It's just against the pole. It's not playing against another agent trying to knock the pole down or anything like that, right? It's just one agent. So I want to get into all that stuff. So that can be postponed for the third talk. You guys like that idea? Yeah. I'm so surprised. Okay. So do you want to do questions now? Or should I walk through? Should I get through a couple slides here?
So maybe you have to see how far you get.
What's that?
Do a bit, see how far you get.
Okay, I'll tell you what. I'll do 4 slides really quick just to get an overview. Yeah, we already talked about this guy. So this is the paper from 2015. 2013 and 2015, this revolutionized RL. Suddenly deep RL was a thing. It was not a thing before. DeepMind, this is what made Google want to buy DeepMind as well. They applied deep learning to Q-learning. Combine those to make DQN. And it was a big deal. This happens to be the Q network they used. Convolutional, fully connected, leading to all the different actions would have a Q value coming out. So you just pick the highest Q value. You learn your Q function using a deep learning network. I mean, who thinks that a first-year CS student could solve Pong? Or who thinks they couldn't? Right? Pong's not that hard, so what's the big deal? Who cares? You can solve Pong. Anyone know why it's a big deal?
Problem space is bigger.
One algorithm solved all these games. All the ones on the above the line. One algorithm. One set of hyperparameters. They did not tune it. They just plugged the same algorithm into game after game after game. Boom, solve that one. Boom, solve that one. That was totally a new thing. That is revolutionary. This is why it's revolutionary. Not because they solved Pong. Pong is stupid. Easy. But this is a big deal. Now, they didn't use the same network on all the games. They plugged, and I mean, it was the same design. They trained it on the game, evaluated it on the game. Then they moved to another one, trained it on the game, evaluated it. They weren't trying to make one network that solved all of the games together. But I'm saying it's the same design, same hyperparameters, most of the games. Okay, that was the accomplishment. So they combined Q-learning, deep learning, and then they added this thing called experience replay, which is a bit of memory to remember some experiences. Okay. So this is what I would get into if I guess we did the other talk. I would get into this in more depth. So I guess I could tack this onto the other talk. Can we go to questions?
So you've shown that reinforcement learning is typically very computationally expensive to train, and how expensive it is to run.
It can be well, it depends on the situation, but it can be way more efficient to run. I mean, generally these systems, you end up with a neural network, right? Like how hard is it to train on ImageNet versus when it's trained and you just pull it in one? So it doesn't have to be expensive to run. And it doesn't have to be expensive to train depending on your problem space, right? You have a smaller problem space. Go just happens to be very expensive.
So you showed a number of them. Most of the examples are about games. Are there examples where hardware was used in something in real life that's not just experimental? Like you said, robocards are not yet doing well. You use hardware. So is there an example of something that actually did well and is not simulatable?
Okay, so there's, and is not simulatable, you said?
Yes.
I don't have an example off the top of something that's not simulatable and done well. That's true. I think I'm.
That's not a game.
Okay, well, I think, like I said, I think Google Duplex, the phone system, where I don't know if you guys saw Google Duplex. It can it can make a reservation and it can handle conversation. So the act of conversation dialogue can be considered an RL, can be framed as an RL problem, and I think that could be a good example. I mean, there's really not much examples in the real world. So I saw one talk where this guy said he made a garbage picker that would go through the recycling and pick things, and that was all using reinforcement learning. That was a recent example. But I mean, there's not that many, right?
One of the classic examples is also like Roomba. If you're looking at SLAM, that was actually framed as a reinforcement learning problem as well. So you're trying to map your environment, and the only feedback you get are the distance from your sensors. You're trying to map your environment. So you can actually frame a lot of problems as reinforcement learning, and like Roomba is a very good example of something that's actually in our big lines, and it's kind of like using a similar sort of framework for doing all of this.
I assume they did it through
No, just saying that there was a lot of work done similar, just to kind of improve the algorithm. So it's a SLAM-based method, so kind of developed in the reinforcement learning field. So the art of mapping.
Before I knew any reinforcement learning and self-driving cars and what they actually do, I had this vague idea that they were using RL and self-driving cars. It sounds like not at all.
Would they use RL and self-driving cars? Probably not. I agree with you, Bruce. I think definitely not end-to-end, right? There might be some scope for training some small components, but it's such a safety-critical thing, And there's the way, from what I understand, the way they break down the self-driving problem is in very many little steps, and I don't really see RL applying in that way with the current generation of RL. So I don't think so.
In one of the earlier slides, like you brought the multi-armed bandit, and so these are like slot machines, and in general, slot machines are supposed to be, at least in theory, purely random. So what kind of reinforced learning can you get with pure random outcome processes where like the reward is random and
Okay, yeah, sure. So RL can handle, or at least some RL algorithms can handle scenarios where the rewards are random, where transitions have some randomness in them. In this particular scenario, you're talking about the slot machine, the multi-armed bandit. So in the theoretical multi-armed bandit, like I talked about, is not like the real casino. In this example, every bandit has a different probability of winning. In a real casino, they should be all the same probability, very small. But in this scenario, each bandit has a different probability, but we don't know it. And we're using this method to try to estimate what it is.
we have time for one last question.
That's probably.
Okay, you're welcome to chat with me afterwards. And I'll plan to schedule another talk with you guys.
Yeah, really. A couple of announcements. So as you leave, if you could put chairs back on the rack, that would be extremely helpful. And thanks for coming. Thanks for arriving. Everything wasn't very easy to prepare, so we really should thank the speaker again.
Thanks so much.